Welcome. Previous class I was discussing about pericyclic reactions. On that time I discussed about that introductory part of pericyclic reactions. That is that MO representations of any organic molecules that I have discussed. So we can make these MO diagrams for any organic molecules by by knowing this four concept, that is number of carbon atoms is equal to number of p orbitals or lobes or number of orbital energy, or that orbital energy, that number of orbital energy is present. Okay, that is equal to number of carbon atoms. First point. And second point is that if psi n is odd, then terminal lobes have same signs, and if n is even, then the terminal lobes have the different signs. This is the second point. And third point is that if psi n and n is odd, then we have the plane of symmetries and C2 axis is absent, and if n is even, on that times plane of symmetry is absent but C2 axis is present. And fourth point is that nodes, the positions of a place or where the getting of electron density is 0, that is psi n, where nodes is equal to number of getting that nodes, that is n minus 1. So applying these four, we can make that orbital energy representations of any organic molecules. Okay, so these things I have discussed in the previous class, and what we have left is that here see that four energy levels, because four atoms are there. So I can draw here 1, 2, 3 and 4. Okay, now the important thing is that since here that in a reactions, like only that orbitals will participate which are HOMO and LUMO. So you know that HOMO and LUMO concepts. Okay, because that frontier orbitals only participate in the reactions, because we have all these energy levels, but these all energy levels, they are not participate in the reactions. Only frontier orbitals will participate in the reactions. What I said, that only frontier orbitals are participate in a reactions. It means that if you know only that if you know about of the frontier orbitals, then we can understand that how the reactions is. We no need to understand all that orbitals. Here we have mentioned that four energy levels are there, because we have the four carbon atoms, but that participating orbitals are only the frontier orbitals only participate in the reactions. So what are the frontier orbitals? So that frontier orbitals are, these frontier orbitals are, what are the frontier orbitals? That are HOMO and LUMO. So these are the frontier orbitals. Only these participate in reactions. What do you mean by HOMO? That is highest occupied molecular orbitals. And what is LUMO? LUMO says that lowest, and U for unoccupied molecular orbital. It means that we should know that one is highest occupied, that is occupied, and that has to be highest. Another is lowest, and that has to be unoccupied. So these two only the participate in the reaction. So from here, although we have done that four energy levels, but we will look that which are the highest and which are the lowest. Okay, highest occupied and lowest unoccupied. Okay, so we have to fill the energy first. So how you fill that electrons? So look this molecule. So we are drawing that MO representations for 1,3-butadienes. Okay, in these 1,3-butadienes, what we will look that only the pi electrons that will show the MO diagrams. Okay, so how many pi electrons are there? This is 1 and 2. So 2 pi electrons is present. So 2 pi bonds. 2 pi bonds means 4 pi electrons are present. It means that I will draw that 4 pi electrons here. where it is, yes, here. So 4 pi electrons, one is 1 2 3 and 4. Okay, and this is after heating. Okay, if you give heat and then this will happen. Okay, so now from here what we understand, that we look that frontier orbitals only participate in the reactions. It means one is homo and lumo. You will check here. So homo is what, which is highest occupied molecular orbital. So we have that 4 from that which is highest, and that should be occupied. So 2 are there and that should be highest. So this is the highest, this is not highest, this is the highest, means energies are this order, this is the energy order. So highest means this, so this has to be the homo, because that should be highest and that should be occupied. So this is homo. Now this is homo. Okay, now which is the lumo here, that is lowest unoccupied molecular orbital. So we have the 2 the which are unoccupied, but that we need, that should be lowest. So this is the lowest, so this is going to be the lumo. Okay, so this only, if you know the knowledge about of only these 2 orbitals, then we can draw, we can analyze the reactions. Okay, so because only these are the frontier orbitals, and these only participate in a reactions. These not participate in reactions. So only if you know the if you know only these 2 orbitals, that is homo and lumo, then we can analyze the reactions, because these are the frontier orbitals, and these frontier orbitals only participate in reactions. Okay, now it is after heating. Now if we give the photochemical conditions to here, photochemical condition means H nu, then what happened, that one will shift it, means one will do the transitions. So what happened, again we will draw that for energy levels, this for, so these are already filled. Okay, and one will transitions to above, so this one will that. Okay, now here what is the, which is the homo and which is the lumo. So homo means highest occupied. So this is also occupied, this is also occupied, this is also occupied, but we need that highest. So this is the height. So this is going to be the homo. And lumo is, that is lowest unoccupied. Only one is unoccupied, and this is also lowest, because this is the lowest, because that should be unoccupied. Only one is left which is unoccupied. So this is going to be the lumo. Okay. So for this is at photochemical conditions. That is photochemical conditions. So for photochemical conditions, that our frontier orbitals are, these are the frontier orbitals. So if you know only these frontier orbitals, then we can easily understand that we can easily analyze the reactions. We no need to know about of this, we no need to know about of this. Only frontier orbitals are needed for to analyze any organic reactions, because only these frontier orbitals that participate in the reactions, other orbitals will not participate in the reactions. Okay, so I will now go to the we will discuss now the type of that is pericyclic reactions. So these are the, what I discussed, these are the general concept that will apply in every pericyclic reactions. Okay, so now we will discuss one by one all pericyclic reactions. So what I said in the before, that pericyclic reactions, that this first is electrocyclic reactions, cycloaddition reactions, in reaction, and sigmatropic reactions. So first we will go with electrocyclic reactions, then we will go for cycloaddition reactions, then we will go by one. Okay, so first topic will be electrocyclic reactions. So we will discuss on electrocyclic reactions. So whatever I use the concept of that is representations of molecular orbitals. The same things here also we will apply in cycloadditions, also apply in all the reactions we will apply. Okay, that's why I discussed that the general concepts. So these things we again discuss here. Means I will just do very shortcut because I already discussed that things. So for electrocyclic reactions, what it that mean electrocyclic reactions? So the important things for electrocyclic reaction is this is a unimolecular reaction. This is a unimolecular reactions. It means that only one substrate is used or present. So unlike in the previous class, I have discussed that one examples where I says that two substrates were present. What I discussed in the previous class, that is like this we have, and we have this, and that I did that. This is going to shifted here, this is going to shifted here, this is going to shifted here, and we see that this has four. Okay, this has four. So this here the two substrates is used here. This is one substrate and this is one substrate. So here what how many substrate? Two substrate we have used. So this is not a example of electrocyclic reactions. This is an example of a cycloaddition reaction that we will discuss after completing of electrocyclic reaction. This is examples of cycloaddition reactions. Okay, so now for electrocyclic reactions, but it says that this is a unimolecular reactions. It means that only one substrate is used. Here two substrates is there, so this is not a electrocyclic reactions. Okay, so what things is there in the electro? Only one substrate is there. So that examples like you see that this one. Okay, here let's say here we have, here we have, here we have. Now if you give the heat here, okay, now if you give the heat, then what will happen that only one substrate is present. So here only one substrate is present. This is the example of electrocyclic reactions. Okay, so what will happen here? Let's say it will shifted to, so if we give the heat or photochemical conditions, that things we will discuss while discussing about of this electrocyclic reactions, that if we give heat or photochemical conditions, what will do that it will shifted to here, and it is going to shift here, and it is going to shifted here. So what things it occurred? What things it has occurred? Let's say here that this, okay, so what that this shifted to this bond shifted to here, it means that here it will comes, and this shifted to here, okay, and this shifted to here, so that is going to mix like this. Okay, so this has break and this has form, this is break, this form, and this is made to sigma bonds. It means that what things here we observe, here we have the 3 pi bonds, here we have 3 pi bonds were there, and what this is the reactant, and the product what you see that so okay, so the one thing also I would like to discuss, because this is the past example. So while doing that electrocyclic reactions, any pericyclic reactions, what intermediate will form, that is cyclic transition state will form. Okay, not intermediate, cyclic transition state will form. So first I will make the transition state. Okay, so sometimes this transition state they will not make, simply they will give the product. So although this is the past class, so I will make that transition state also. So what transition state will form? So this is going to be like this. Okay, and what is that? here this is breaking, and here it is forming. This is breaking, and this is also breaking, and here it is forming. Okay, so what is that? So forming means here it is, so forming, so you will do the dotted lines like this, because it is breaking and forming that is happening here. Then here is breaking, and here we have that. Okay, so this type of transition state will form. Okay, this red line, so red line, a red dotted line, a red dotted line was breaking, and this yellow lines, yellow dotted lines shows that, no, red dotted lines shows that forming bond, and yellow dotted lines shows the breaking of bond, breaking of bond. Okay, so this type of transition state will form here. Okay, so this is a cyclic transition state. Transition state will form. After that, we will make that product. So this is remain as it is. Okay, now this red lines will form, so this will forms, and this will forms, and here we will have like this. It means that how many? 1 2 3 4 5 6. So this also is equal to, so this will form, and that also they simply write like this. Okay, so this is the product, so you will get. So here what things we notice, that only one reactants or one substrate is used, and we will get that if we give the heat, then cyclic transition state will form. After that we will get the products. Okay, so this is a type of that electrocyclic reactions. So in electrocyclic reactions, what we see that this is a unimolecular reactions, and only one substrate is used. And what things you have noticed here, that here we have the 3 pi bonds. Here we have 3 pi bonds is there, and what we get that finally what we get that here are 2 pi bonds and 1 sigma bonds we get, because this is also a new bond has formed, and 1 sigma bond. It means that this is, we can say that 2 pi bonds plus 1 pi bonds, that was that, because 3 means 2 pi plus 1 pi. Okay, that is going to form the 2 pi bonds and 1 sigma bonds. It means that if you compare the energies, there what that this and this will cancel. It means that 1 pi bond is forming the 1 sigma bonds. Okay, it means that what we see here, that pi bonds is forming a sigma bonds, and what we know that this pi bond is weak bond. Weak bond means that it is having that high energy, because if it is high energy, it means that is weak, because every electrons wants to stable, they are stable at the low energy. So this is having that high energy. Weak bond means high energy, whereas this sigma bond which is forming, that is a strong bonds. So strong bonds means they may be strong bond means they are in the low energy, that's why they don't want to break. Okay, so they are low energy. So from what that electrons is transferring, so from here what we see, that electrons transfer from high energy to low energy. So that's why that Even if you give heat, then these reactions will proceed and this will form. Okay, so what you notice here, that pi bonds are forming a sigma bonds. So here we see that pi bonds are breaking and forming a new sigma bonds. So in electrocyclic reactions, we will see that there will be a formations of a sigma bonds. Okay. So in electrocyclic reactions, we will see electrocyclic reactions. A sigma bond will be formed. Okay, so this is the electrocyclic reactions. What you say, that only one substrate is there, and next is that here sigma bonds will form, and what that it should be that the substrate should be in the conjugations. Like you see here, that this is in the conjugations. It means that the substrate should be in conjugations. Okay, so then only this electrocyclic reactions will occur. So these are the points that is needed for to be a electrocyclic reactions. And what things, and what you say, that you have given the heat. So what you say, that heat or photochemical conditions are needed to proceed the electrocyclic reactions. Okay, so these are the some points about of that electrocyclic reactions. Now we will see that how that sigma bond is forming. So what we see here, that sigma bond is forming, that we see. Now we see that how it is formed. Okay, so what we say, that in the past class itself I said that in carbon chemistry or in organic chemistry, p orbitals is there, and these p orbitals, what that they will make a new sigma bonds, because this pi bond is breaking and sigma bond is formed. So let's, if I take the examples here, let's take the example. Suppose we have discussed this one, so let's go through this example. We have like this. Okay, now we are giving heat. After we heat, that is what we see, that this will break and this is forming, and what we see in here, that is going to be like this, and this is shifted to here, and this is forming to like this. Okay, that we see here, and this is also equal to this one. This is also going to be like this and this. Okay, this actually okay, so this one, that what it is actually, so this is forming this one. So what you see, that here the pi bonds will form a new sigma bonds. This sigma bond has formed. Sigma bond has formed. So how this has formed? So from here, what we see, that in the previous class, that MO representations of any organic reactions that I discussed, that there what we said, that the frontal orbitals will participate in the reactions. So how will you represent that the MO diagrams for this substrates? So it, how many orbitals, how many carbon atoms are there? 1, 2, 3, 4, 5, 6. It means that while doing that, what we look here, the arts will be like this, and here that 6 carbon atoms are there. So that will having that 6 energy levels, because energy level equal to number of carbon atoms. So 1, 2, 3, 4, 5, and 6. So this is psi 1, this is psi 2, this is psi 3, this is psi 4, and this is psi 5, and this is going to be the psi 6. Okay, now thing is that we don't need to look all that energy levels, because only frontiers orbitals only participate in the reactions. We can draw all these things, but what that main thing is that frontier orbitals only participate in the reactions. So it is very good to say that we will just represent that only that frontier orbitals. Okay, so if I draw here, then six lobes I have to make like this, like this, like this. So that things I will not do again and again, because that I have discussed in the past class to understand, because sometimes questions also asked by making the lobes also, but that things are not needed always to do to analyze any reactions. So we just need that frontier orbitals. So this one, then what I do here, so how many pi electrons make that here? 1, 2, 3, 4, 5, and 6. Okay, so now how many pi electrons are there? 1, 2, 3. So 3 pi bonds means 6 pi electrons are there. So make that 1, 2, 3, 4, 5, 6. Okay, this is on heating. Okay, now here which is HOMO and which is LUMO? So HOMO is, this is the HOMO, that is highest occupied HOMO, and this is going to be the LUMO on the heating. Okay, now if we give that photochemical condition, then transitions will occur. So that is going to be like this: 1, 2, 3, 4, 5, and 6. So one will do transitions, make this is shifted to here, that will remain as it is. 1, 2. So this is going to do the transitions from here to here. Now for this, which is HOMO, this is the highest occupied, that is, this is going to be the HOMO, and this is going to be the LUMO. This is going to HOMO, and this is going to be the LUMO. Okay, so only this frontier orbitals only participate in the reactions, means we should focus only on the this HOMO and LUMO only. Okay, so now how will you analyze this? So for that we look that p orbitals, that rotations is needed, that in which directions that p orbital will rotate while making a sigma bonds. So what I said here, okay, so the forming a new sigma bonds, because the sigma bond is forming. Okay, so forming a new sigma bonds, the p orbitals, that is, which is in the, that actually they are in the pi orbitals. Okay, that p orbitals in pi orbitals. Now that p orbitals making a sigma bond, so the rotations of p orbital is important to understand that, because that was in pi orbitals. Now this pi orbitals is now making a sigma bonds. Sorry, so the p orbitals, the rotation is needed. So for me a new sigma bond, the p orbitals will rotate. That is in two ways. One, it can rotate in same directions, or also chances is that it can rotate in different directions. P orbitals. Why I am saying p orbitals? Because that what we see that actually this HOMO and LUMO, they will participate in the reactions. So that p orbitals, what we see here, if we look that, so okay, first we will discuss on that. Same directions means that we will say in pericyclic reaction, electrocyclic reaction, that we say that cone rotatory. Okay, so if they are rotating in the same directions, so on that we are saying that cone rotatory. And if it is rotating in the different directions, then we are saying that that is a dis rotatory. Okay, So now just try to understand this. For this we have, okay, here we have this. So what things we say that this one, that the frontier orbitals only participate in the reactions. It means that here these are the frontier orbitals, because from this the participating orbitals only do the reactions, and that participate orbitals are called frontier orbitals. That means they are the HOMO and LUMO. Okay, so what we know that for a uh, uh, for a electrocyclic reactions, if it is a unimolecular, then that HOMO is considered to HOMO is used to analyze the reactions. Okay, so this point you have to note that for unimolecular reactions, or say that one substrate is present, then HOMO is used to analyze the reactions. Okay, so this is the very important points, that if it is a unimolecular reactions like electrocyclic reactions, then HOMO is used to analyze the reactions. And if it is not unimolar, like say cycloaddition reactions where two substrates are there, that is bimolecular reactions, on that times both HOMO and LUMO is used to analyze the reactions. But if it is a unimolecular, that is one substrate is present, on that time HOMO, we will only consider the HOMO to analyze the reactions. So here which is the HOMO? This is HOMO, and this is actually Psi3. Okay, for the heating. And for that photochemical conditions, this is the HOMO, and this is going to be the Psi4. So this is on heating, and this is the HOMO. Okay, for heating, and this is that HOMO for photochemical conditions. This is the HOMO. So this Psi3 for heating, this is analyzed to study the reactions. So what I say is that here, that for analyzing, for study that reactions on heating, what we look that Psi3. Okay, the Psi3 functions will help us to study that how the reactions will happen. Now this is Psi3. So Psi3 means what we see, that this is Psi3. So 3 is odd. So in previous class I says that if it is odd, then that have that terminal lobes will have that same sign. So what is here? So you look that here may be the one terminal lobes for this. Okay, and here also again this is the terminal lobes. These are the no terminal lobes. Here also lobes are there. Okay, here also lobes is there. Here also lobes is present here. Here also lobes is present here. Here also lobes is present here. But what we say that we look only the terminal lobes that I have discussed in the previous class. The terminal lobes is important. Okay, so and that terminal lobes, what I say that if psi n and n is odd, then they have that same sign. So these terminal lobes, what that now for heating, what we are saying that for heating that Psi3 is HOMO for us. So for heating Psi3 is HOMO. So that we should analyze it now. So now that Psi3 is, since this is odd, so odd means that the terminal lobes have the same signs. It means if it is positive, then it is negative, then this is also have to be positive, and this has, sorry, this is negative and this is positive, because this have the same lobes. Okay, so what you see in here that just erase it. Okay, so now because this and this have the interactions, because this is minus and this is also minus. Okay, so for heating that psi 3 is homo, so this terminal lobes should have the same sign, means that this is down minus, so this in the here also this has to be minus, so that same will be do the interactions. Okay, now what I am doing that, now what I will do that, this p orbitals, okay, they will rotate so that new sigma bond will form. Okay, so because this will form the sigma bond, so they will rotate. That rotation can be two ways, either same directions or in the different directions. Now, so what I will do that, if I will do that cone rotatory, it means that same directions. If I do that cone rotatory, means that same directions. Or this one we can draw, sorry. So this one actually we can draw. Sorry class, this one we can draw like this. Okay, not like that. This one we can draw like this. Okay, so this one and this one, these are the terminal lobes. And what we see that if it is positive and this is negative, and so the terminal lobes for odd number, then they should have the same sign. It means this is positive, again this should be positive and this should be negative. Okay, so that p orbitals will represent like this. Okay, so for homos, not like this, we will rotate like this. So we can draw that, we will draw the p orbitals in this manner. Okay, because this have that interactions and this have the interactions. So that since this is odd, so the terminal lobe should have the same sign. Okay, now we will do that cone rotations to it. So when we do that cone rotations, then what will happen that we has to do that in the same directions of both terminal lobes. We will rotate in the same directions of both the terminal lobes. It means that if I rotate this in a clockwise, then this one also I have to do the clockwise. Okay, so rotate it, then I will draw here. This is the, so this one I am rotating like this, then this one I am rotating clockwise. It means that this is positive and negative. So if I rotating like this, then this is going to be becomes like this. So this positive will comes above and negatives will be go down. Okay, now this one also I should rotate in the same manner. So this is also the positive will go up and negative will come down. The positive will go up and negative will come down. So now we will look that here this positive and negative, they will have any interactions? No, because what is this? I say that for the lobes, the orbital lobes, that if they have that same sign, then only they will make the bonds. So here they will not able to make bonds, because what I say that positive make bond. Okay, or negative negative make bonds, but positive negative or negative positive not make bond. So this is going to be negative positive, so no bond formations will occur. So here no bond, so no new sigma bond formed. So if you do that cone rotatory to this, then what we say that we can get any sigma bonds. So other the chance is that we can do that this rotatory. Okay, so if you do that cone rotatory, then we are getting no sigma bonds. So other will be we have to do a this rotation, this rotatory. Okay, so for this case, how we look at again make the bonds now. Okay, so now this is like this is like this, and this is like this. So now if I make that this rotatory means, what I said, this rotatory means if one I'm rotating like this, then other I will rotate like this. It means it is clockwise, then this has to be that anti-clockwise. Means that one terminal lobes, if I am doing that clockwise, one terminal lobes clockwise, then other terminal lobes in anti-clockwise. Okay, so what I seen here, this if I am rotating in a clockwise, so what I will get here, I will rotate like this, then this is going to be the above it will go the positive, and down is going to be negative. Positive, and down is going to be down, above is going to be positive and down is going to be negative. But now this one, for this case I have to do the anti-clockwise. This I am doing clockwise, then this I have to go the anti-clockwise. It means I have to rotate in a this I am rotating like this, then this I will rotate like this. It means, so this one I am rotating, this one I will rotate anti-clockwise. It means that the negative will go off and positive will come down. So from here what we see that we are getting that negative means that here that bond formations will occur. So here what you see that bond formation, that is new sigma bonds, new sigma bond formations occur. So what you see that if this is the substrates, then on cone rotatory we are not getting a bonds. Okay, we are not getting a new sigma bonds, but if we do the dis rotatory, then we are getting a sigma bonds. Okay, so that things we will look for different substrates, and we will give a tricks that where that bond will form, whether this rotatory or the cone rotatory. Okay, now we'll take another substrates. This is the one type of substrates. So here what you say that 1 2 3, so 3 pi bonds is used here. Sorry, here 3 pi bonds is present, 3 pi bonds. Now we will look at other things. Let's take that other substrates. Let's we have this. Other substrates is like this. Let's say so there should be a conjugations. Okay, so I will make this. There should be a conjugation. So here conjugation is there. Now what I will do that for these substrates, if I give the heat, then what will happen? Let's see. If I give the heat, then what will happen? If you check there, if you check that, then this is going to rotate here and this is going to rotate here. Okay, or for that we have to make the photochemical that things also, so I will do it later. The same things for these substrates. Okay, for these substrates we will check that this we have checked in a heating, and other is that photochemical conditions that we have left. First is by heating we get this one, Now we have that photochemical conditions, and for photochemical conditions, now that analyzing orbital is homo, because this is a single substrate. So now that homo is changed, that is going to be psi 4. For heating, that homo is psi 3, but for that photochemical condition, that homo is now the psi 4. So the same substrates, okay. Now for photochemical conditions, that is H nu. Now that homo is psi 4, because you see here that for heating, that homo is psi 3, but for photochemical conditions, that homo is changed to psi 4. So now we will go through psi 4, and what is said that this is the even number, and if it is an even number, then what is said that terminal lobes have different signs that we discussed in the first class. So now make the substrates. So this we have, this we have. Okay. So now that since psi 4 is that homo, so that have the different signs. It means that if I draw the orbitals here like this, then they have the different sign. It means that if it is positive and if it is negative, then this has to be negative and this has to be positive, so that they have the different signs. Okay. If they have here positive, here negative, then they have the same signs, but we need the different signs. Now we can do the two rotations. One is con rotatory. It means that we will rotate in the same, both the lobes in the same directions. Another is we will do the these rotations, and we will check that where bond is forming. Okay. So for con rotatory, what we see here, if we rotate it, then we has to rotate both the terminal lobes in the same side. If we are rotating clockwise, then also we do that clockwise. Then what we will get here, so what we will get here, that is going to so this I am rotating clockwise, so I rotate here clockwise. This one also I rotate in the clockwise, and if above is positive, then that will say above positive, and this is going to be negative, and this is going to be the clockwise, so this is going to be the negative, and now this is going to positive, because I am doing the clockwise both the case. So what we see in here, that both side negative means bond formations will happen. So new sigma bond form here. But now if I do the this rotatorily on this case, then I will make that. Okay. So what I do that, I have to rotate one in the clockwise. Let's see if I rotate this. Okay. Now if one I'm rotating like this, then another I have to rotate it anti-clockwise. So one, if I rotate clockwise, then this is going to be positive, this is going to be negative, and anti-clockwise, that so this positive will go up and negative will come down, because I am rotating this one that directions. So this is going to be negative. So here that bond formation will not occur. So no sigma bond will form. So what we see in that substrate is same for photochemical condition, another is on heating. Okay. Since that homo is changed here, that homo is here that psi 3, whereas here the homo is psi 4 for photochemical conditions. So since that homo is changed, so on heating, that bond formations is happening on the con rotatory. On the this rotatory, that bond formation is happening, where here that no bond formation is happening for con rotatory. This rotatory bond formations is happened, and new sigma bond is formed on heating. And the same substrates on photochemical conditions, since that homo has changed, here that what you see, that con rotatory bond has formed, but this rotations no bond formation is occurred. Okay. So what is seen here, that if substrate is this, if substrate is this, then if we do that heating, then on these rotatory bond formations occur. New sigma bond form. And on photochemical conditions, H nu, that is on con rotatory, new sigma bond has formed. New sigma bond formed. Okay, so if you are giving a heating, then this rotatory only the new sigma bond is forming. On this rotation, sigma bond is forming. And if you are giving the photochemical conditions, on that case, on con rotatory, that new sigma bond is forming. So if the substrate is this, then if you give that heat and if you do that con rotatory, then there will be no sigma bond will form. Okay, at the same time, if you are giving the photochemical conditions and if you are doing the dis rotations, then no new sigma bond will form. So sigma bond will form only if it is heating, then on con rotatory, and if it is photochemical condition, then so this is dis rotatory, and if it is a photochemical condition, then con rotatory, that new sigma bond will form. So these things we will that I will give the tricks. Now just for understanding, I have said that where the bond formation is happening. Okay, that things I will sum up and I will give a tricks. From that we can easily say that where bond formations happen and where bond formations will not happen. So this is the one substrate. Now we will look for that another substrates. Let's we have the substrate is like this. Okay, here that means conjugation is there. Now if we are giving the heat, then how that this will happen? So for that again we have to make that MO diagrams. So first we will make that MO diagrams. So if we make that MO diagrams, then how many carbon atoms are there? 1, 2, 3 and 4. So 4 carbon atom means 4 energy levels I will draw here. That is psi 1, psi 2, psi 3 and psi 4. Okay, so similar I will do that 1, 2, 3 and 4. Now how many pi bonds are present? 2 pi bonds. So I will make 2 pi bonds, means 4 pi electrons. Okay, and this is heating. Now we will do that photochemical conditions. Means that if I give that photochemical conditions, then what will happen? That one will shift it. So this is going to like this and this is going to shift. Now what we see that this is at photochemical conditions. Okay, now the same things we will also look here, that for HOMO, this is the HOMO here and this is the LUMO, and for this is the HOMO and this is the LUMO. So for since this is electrocyclic reactions, one substrate is used, so HOMO is used to analyze the reaction. So for this case, that our HOMO is important. So for this HOMO is psi 2 and for this HOMO is psi 3. So now we look at heating and photochemical conditions. So first is heating, then for that HOMO is, that is psi 2. Now here photochemical conditions, that is psi nu. So here that HOMO is what? HOMO is psi 3. Okay, HOMO is psi 3. So what we will do that, make these bonds. This we have, So our need is that here side 2. So if it is even number, then the terminal lobes have the different signs. So make the terminal lobes here, this one, also this one. Okay, here also make the same things. Okay, so here homoid side 3 means odd number, means that the terminal lobes have the same sign. So this is even, so different. This is odd, so that will go into the same. So how will make that? If it is positive and negative, then this is different, so this will have the negative and this will have the positive. But for this case odd, so same sign. So if it is positive and negative, then this is also has to be positive and negative. Okay, now we will do that con-rotatory and dis-rotatory. Okay, so one we will do that con-rotatory, another we will do that dis-rotatory. So we know that con-rotatory means same side we will rotate. So if I rotate this one, so for this con-rotatory, I will rotate the, if I am rotating this one also clockwise, then I also has to do this also in a clockwise. So this is this one. So if I rotate in a clockwise, then what it will when it becomes. So if it is positive, then this is going to be the positive and this is going to be negative. Now this one clockwise also, then this is negative and this is positive. Okay, so what we see here, that bond formation is happening. So here what you see, that new sigma bond formed. But if I am doing that this rotated, it means that if you want, I am rotating one like this, then other I have to rotate like this. It means so one I am rotating like this, it means that one is positive, negative. Other I have to rotate like this, means positive will come here and negative. So here that no bond formation is happened. No new sigma bond form. So what we see that here on con-rotatory bond formation is happening and dis-rotatory bond formation is not happening on heating. Okay, now we will look the same things for photochemical conditions also. So here also we will look that con-rotatory and also we look that dis-rotatory. Okay, so first make that separates. So con-rotatory means if I am rotating clockwise, then also I have to rotate this also clockwise. So this is going to be a positive, above positive and comes down the negative. So this is also that positive and negative, because I am rotating this also in a same directions. Now this rotatory means I will rotate in a different directions. If I am rotating one like this, then other I have to rotate like this. It means that if it is positive and negative con-rotatory, then this is going to be that above will go negative and down will go to positive. So what you see here, no bond formation is happened, because that positive negative, no bond formations, no new sigma bond form. But here what you see, that new sigma bond form. So what we see in here, if this is the separates, then what we see here, that on con-rotatory we are getting the bonds on heating, and for photochemical conditions where that here on this rotatory we are getting the bonds, here we are not getting the bonds. So that's we look that what is seen, that for heating condition, on heating and on photochemical conditions. Since heating and photochemical conditions, that psi is changing, here psi 2, here psi 3. So that's why that in heating, that on con-rotatory we are getting the bonds, whereas on photochemical condition on this rotatory you are getting the bonds. But how that all the times we don't need to do all these things because it will take times, and in exams we don't have the times to do all these things. So we have the tricks that will gives. So just I will do that. After that I will give the sum up. Okay, so for this, if this is the substrates, if this is the substrate, then what, on heating, if you are heating, then where bond formations happen, on heating, conrotatory, on heating conrotatory, the new sigma bond form, and if it is a photochemical conditions, then where I am getting the bond, on this rotatory, new sigma bond form. So this is the one substrates. Another substrates what you seen here like this one. This one also I have said that on heating, and another is on photochemical conditions. So if this is the substrates, then where I am getting the bonds that I have said here. So if we are giving heating, then this rotatory, heating, then this rotatory new sigma bond has formed. And if you are giving the photochemical conditions, then con rotatory new sigma bond has formed. Okay, so that, let's see that con rotatory. Okay, so if you observe that two substrates, okay, if you observe that two substrates, one is this, another is this, two substrates of this substrates and this substrates, what we seen here, that here we have the two pi bonds. Okay, so two pi bonds, here we have that two pi bonds. Here how many pi bonds is there? 3 pi bonds is there. So if you observe it carefully, then what I have seen, that aromatic characters. So aromatic rings, what we seen, that odd number of pi bonds, then that is aromatic characters. Okay, so odd number of pi bonds, odd number of pi bonds. And anti-aromatics, what I say here, that is even number of pi bonds, even number of pi bonds. So what the same things you will apply here, that here 3 means odd, and here we have the 2 means even. So what we seen here, that aromatic means what we say, that 4n pi electrons. Oh yes, so here what we seen, that this here that tricks how we leave that odd, then this the odd, then that will falls in this 4n plus 2 pi. Okay, where n is equal to 1, 2 and 3. This is the aromatic character. So if that it has that odd number of pi bonds, then that will follow this 4n plus 2 pi, and that we say that this is the 6 pi. This is the what we say, that 4n plus 2. So if n is 1, then 4 1 plus 2, then that we can say that 6 pi bond. Okay, 6 pi, that is called, we can say 6 pi. And now if it is even, on that case what we say, that is for n rules we will apply here for n pi electrons. So on that, say what you say that 4 pi, where n is equal to 1 2 3. So here we say that this is 4 pi. So that simply what we say that even number of pi bonds, even number of pi bonds, and here that odd number of pi bonds. Okay, so that is what we say that if for n, if n is 1, then that is going to be 6. So that we say that 6 pi bonds, and this is going to be that 4 pi bonds. So trick is what? So we will make a notes here. So one, I will say that system. Let's say this is the system. Okay, now we here we rotate that. Okay, now we will look that whether this is okay. Now if it is cone rotatory, and this is, now we say that this rotatory. Okay, so systems are, what are the systems are there? We have one is 4 pi system, another is 6 pi systems, because this one, this 4 pi means not that always 4 pi means even, and this is odd. Okay, so for even, so what we say that this what we say that this is that